Okay, this is a response video to my conclusion to the Continuum hypothesis series. And this is something in the way of an apology for something I glossed over very quickly. And that would be the issue of 0 times 2 to the Aleph naught being a reductio ad absurdum, where we could never really solve it. I would like to go into that a little bit more, if we can. Okay, so it's a slight correction. I implied that you could make a case that 0 times 2 to the Aleph naught is either 0 or 2 to the Aleph naught. I would argue that that is correct. However, I didn't really show that last time. What I did show is that it is a reductio ad absurdum, where you can never, let's say you had 2 times Aleph naught repetition cycles of 2 times 2, you would still have 2 to the Aleph naught. In other words, 2 to the power of 2 times Aleph naught is the same thing as 2 to the power of Aleph naught. And then down here you could establish a situation where you would have only Aleph naught zeros. Well, these would cancel, leaving a repetition cycle of 2 times 2 Aleph naught left over. So in a sense, 0 times 2 to the Aleph naught would leave you 0 times 2 to the Aleph naught. Then you could make this 3 Aleph naught and 2 Aleph naught, and you could go on forever and have a repetition cycle where you just got 0 times 2 to the power of Aleph naught and never reduced anything. So it can either be 0, it could be 0, I did demonstrate that, but I did not exactly demonstrate a case where it could be 2 to the power of Aleph naught. What I believe was demonstrated was that if you had a repetition of 2 times 2 times 2 Aleph naught times, that what you would have is something that would be a reductio ad absurdum. You couldn't really solve it. Now, I do want to go into a possible case for 0 times 2 to the Aleph naught being 2 to the Aleph naught. And this is maybe going to be somewhat controversial because it flies in the face of maybe some of the methodology used in calculus, where you're approaching the infinite through the limit at the limit of n as n approaches infinity. Well, here we have maybe a different type of setup. I have on the numerator, I have Aleph naught times Aleph naught times Aleph naught to infinity equaling c. Now notice that infinity to the power of Aleph naught is c, just like 2 to the power of Aleph naught is c. There's a particular property of infinity where if you have the subset of an infinite set, it's the same as the infinite set. So 2 to the Aleph naught would be a subset of Aleph naught to the Aleph naught, and so therefore 2 to the Aleph naught is the same as Aleph naught to the Aleph naught, which would be c. And I'm dividing that by Aleph naught multiplied by itself a finite number of times. Okay, y is less than Aleph naught. Now, I maintain to you that we could establish a situation where our Aleph naughts cancel and become 1. Now that would seem to contradict the idea that 0 times Aleph naught is 0. And actually it doesn't, because I can continue, I can establish that situation where there's a cancellation, but if I multiply by another Aleph naught in the denominator, it becomes 0. And yet, I maintain that I can only multiply Aleph naughts in the denominator some value less than infinity, and the reason for that being that I do not believe, according to my understanding of Cantor, that one can actually divide by 2 to the Aleph naught. Now I know that in calculus we might say, well, 1 over 2 to the power of n as n approaches the limit of infinity. But that says that would be 0. Okay, but that would be as n approaches the limit of infinity. I maintain to you that since 2 to the power of Aleph naught is not discrete, you cannot divide by it. That you cannot divide by a value that is not countable with respect to the number system as we understand it. Okay, that's going to be controversial. What about dividing